So good afternoon, everyone. So before we start, I'm not sure is it heavy rain issue or what, but I've been disconnected for several times. If later on I've been disconnected again, so please spare me some time to connect. Okay. So let me share my screen first. Okay. So let us continue in video processing and video compressions. But for this part, we have video compression, yes, but it is more on the chroma subsampling. So the main video compression would be on in chapter 11. So our final examinations will be on 5th of May. Okay, 2 to 4:30, 2 hours and 30 minutes. Okay, so make sure you're present. This is a face-to-face examination. So make sure you arrange your accommodation and etc. accordingly. Okay. So if you have any question, feel free to ask. And Chia, did you distribute the information for the rest, especially for the that face-to-face examination briefing by Dr. Goh. Yeah. Okay. Everyone, please attend that one. But I think you all are well versed. At least you all been experienced what is face-to-face examinations. So nonetheless, take it as a reminder. So just attend the briefing. Okay, it's important. Make sure you all attend. And yeah, if you have a question, feel free to ask. Yeah. So let us continue. Video compressions. Again, before we start, before every time we mention about compressions, we will talk about the reason why we want to perform compression. The reason only two. Of course, there might be sub reason and might be more than two, but the core reason will be only two, which is to store the data and also to transfer the data. So to store the data, we have a very limited bandwidth. So no matter you have a 5G, 6G, or whatever G it is, the bandwidth is limited. So if you want to utilize the full bandwidth, you have to, comply to the rules and regulation provided by the specific bandwidth. So since the bandwidth is not unlimited, so it's not possible for you to send something else which is very big in a very short time frame. Okay, so that is the reason for bandwidth. And the other one would be the for storage. We have very limited storage. Perhaps this issue, especially the issue of storage, is not so significant in our, computer or any usage. But especially for iPhone user, you all might feel the pain, especially when the storage is going to full and you don't have sufficient iCloud for you to upload and etc. But this issue regarding storage would be a day-to-day, daily basis issue for those, especially during the machine vision. For example, Vitrop, Panda Master, MIE. These company are not really this company, but the customer for this company from time to time they have this issue significantly, especially for those that perform inspection. I think the ABC company in US. ABC is a company name, okay, not random, but it's very accurate. Okay, so they are doing inspections on their semiconductor device. So they need the semiconductor device, even though they already market the product, they still need to keep the device images as traceability. Traceability is new. I wouldn't say it is a new features, but it is sort of um, features that allow the customer to track back whatever whatever this item, I mean, which batch of the production unit have issue, or which batch of the production unit is, I mean, perform better than the original. Okay, so they use the features called traceability. That is why they want to keep all these. They want to keep all the images for such, I mean, some period of time. Okay, so for video compressions, we actually video compression they share a lot of I mean similarity with image compressions is because the video itself is constitute of different frames arranged in correct sequence. Okay, so I believe you all are quite I mean at least like recently like would be quite well versed on the knowledge behind the video and etc. Since you all just complete your lab report, and again remember to submit your assignment on time. Okay, so for video compression is commonly so, thought as thought of being unique to digital, but it is also been around since the early day of analog. Most of the device, for example, the AI, of course, nowadays we always heard about AI, right? Artificial intelligence. But nonetheless, I always want to highlight AI is not deep learning. Okay, deep learning is part of AI. You have to know the set and subset. Okay, so which means this is AI, this is ML, this is DL, okay, something like that. So AI would be the big brother, lah, okay, the umbrella. Inside this umbrella, you have machine learning, which is ML, and inside ML, you have DL, which is deep learning, okay. And deep learning is not equivalent to AI alone, okay. It is only subset, okay, which means your hand cannot represent you, lah. You can represent part of it. You can represent your hand, but your hand cannot represent you, okay. So this is but nowadays, I think it is too cliche to interchangeable these two words. But in fact, it is wrong in terms of knowledge. Okay, so but of course, recently AI is being keep on mentioned and mentioned no matter in whatever field, security, medical, maybe semicon and whatsoever. But nonetheless, actually, artificial intelligence is being I mean introduced to the world, I think is around 1960 something. So, now only become more and more common, and everyone is doing research in AI. I want to do research in AI, so-called the mainstream. Okay, but it take around 60 years to get into mainstream. Okay, so the same thing lah. Okay, the video compression is being introduced very early already. I mean, very early in maybe past 2 decades, but now only people are looking into it because the technology accommodate or associate with the I mean video processing only become part of the mainstream reason here. So compression has just become more sophisticated since then. In this article, I mean this one, okay, this lecture notes, we will take a look at the one of the early strategy in particular, which is the so-called the chroma subsampling. We don't, I mean, in our syllabus, we don't really focus on chroma subsampling, uh, but you should know what is chroma subsampling. Okay, the reason why we have to know chroma subsampling is because we need to know JPEG compression. And in terms of JPEG compression, chroma subsampling is part of it. Okay, and chroma subsampling is more for YCBCR. Okay, it is not suitable to be used in RGB and etc. Because it is about chroma subsampling. So which means in the previous lecture, we already mentioned that human eye is more sensitive to the lumina, which is the luminance, which is the Y channel. And CV and C are so-called the chroma. Chroma is the color, color channel. Uh, I mean, I shouldn't use the word color, but the color sensitivity, okay? But Y is more on brightness sensitivity, okay? So human eye is more sensitive towards the Y channel instead of CB and CR. So CB and CR are both a chroma channel, but for RGB, it is not I mean, different domain. So you cannot apply the I mean, chroma subsampling into G or B or either way or either of the channel in the RGB. That is because the RGB, they need to be, I mean, all the processing should be processed in the same method. For example, if you convert the R channel, I mean, if you apply something else, maybe you downsampling the R channel, you have to downsampling the G and B channel with the same ratio. If you downsampling the R channel, but you did not downsampling the G and B channel, and later you want to fuse it, fusion together, you might have syntax error. Okay. Um, but why CVCR is different? Okay, because one is Lumina channel, another two is Chroma channel. So this is the ratio we are using, which is 422, 411, and 420 to perform the subsampling. And this is the ratio it is lah, whereby you don't have any 412 or any other combinations. So vision specialist has long known that our eye are much less sensitive to color resolution than we are to brightness resolution. So video signal would be separated into lightness or luma component and two color or chroma component, similar to how image can be separated into three RGB component. So basically, you can it's easy for you to convert, especially now with MATLAB and also some other image processing tools. You can easily convert RGB to YCBCR, LAB, um, some other channel, HSV, HSI, and etc. Okay, so this way we can reduce the resolution of the chroma channel while keeping the luma channel at full resolution with very little loss in image quality. Recall back in JPEG compression, we are using YCBCR. The reason why is that we want to maximize, we try to maximize the compression ratio. So if we are using RGB, whatever you perform on R, you need to perform on G and B, right? Okay. So if let's say you are using RGB to perform the compression, no matter you are put it, break it into 8 times 8 pixel block and then quantization and then DCT and etc. You need to perform 3 times. Okay. First of all, it is very time consuming. The second thing is that you still remain the same. I mean, the compression ratio is not to the max. Okay. But for YCVCR, you only need to perform the entire flow of compression, which is uh, I mean, uh, Fourier transform, the quantization, etc. in the Y channel. And CV and CR, you don't need to perform any of these. I mean, all those cumbersome and tedious flow in CV and CR. Instead, you just perform the subsampling as per this ratio, based on the requirement of JPEG, of course lah. Okay. So by using this method, CV and CR is actually being compressed by a greater ratio as compared to this. Okay, because RG and B, they are compressed by the same factor. But nonetheless, if you're using YCBCR, CV and CR can be compressed further as compared to this one. So the luma and chroma component would then be referred as YUV with analog video and YCBCR with digital video as opposed to RGB. So this is the video signal and you have your luma and also your chroma. So chroma is more on, basically luma would be very, very similar to grayscale. This one convert to grayscale. I mean, all the texture, all the edges and etc. still remain in luma channel. But for chroma, it's more on color. It does not really retain the information of the edges and etc. But instead, it keeps all the information of color. For example, the color of the eye, uh, the skin, the eyebrow, and etc. But all those edges, the fine detail and etc. is not really retained in the chroma channel. So that is the difference between the CB and CR, which is the chroma. So Chroma subsampling is a method to reduce the amount of data information of YCVCR video signal. It is different from the spatial and temporal compression used by most of the video compressions algorithm to detect the area of the image in a frame or across a number of frames which they are redundant information that can be described as using less data. This would be I mean this is the core lah. This is the core for next chapter lah. Okay, whereby we will learn about the spatial and temporal compressions. Okay, uh, but chroma subsampling is much more simpler than that because you don't need to bother about what is the spatial differences, what is the temporal differences. You just need to perform the compression in terms of CV and CR or the chroma channel, but according to the ratio, that's all. Okay, you don't need to consider many different um, movement of the character and etc. Is there any movement in terms of spatial or temporal? Spatial is in terms of one image, which means within the one image or one frame, what is the spatial relationship? Temporal relationship is across different frame, across different frame. For example, from 1 second to the next second, first second to the second second, what is the difference? What is the movement of the character that is considered as temporal? Temporal always, temporal always relate with the time domain. Okay, so the chroma subsampling was applied to video codec, which is this one and this one, 264 and 265. So subsampling means the selection of specific pixel information, but not every pixel, from a portion of image to determine the chroma information that is used to represent all pixels. Basically, in the subchroma subsampling, you are actually set the rules. For example, in your lab report, you want to remove, you want to scale down the size of the video, right? So it's up to you what is the pattern for you to remove a particular frame. Okay, so this is chroma subsampling is the ratio, for example, 4:2. So you remove the images, you remove the information of the chroma subsampling based on this ratio. Okay, of course, this ratio reflects something else. So which means either you are removing the horizontal detail or removing the vertical details. Okay. So the subsampling scheme expressed as three-part ratio. That is why you have X, X, and X. So three-part ratio, which is written as JAB. This is J, this is A, this is B. J is basically referring to how many numbers. Usually it's four lah. Okay. So which is 1, 2, 3, 4 lah. Okay. J is referring to this. A is referring how many color in the first row, the top row. B is how many uh, color in the second row. Okay. So if let's say you have 4, 2, 2, usually it's 4 lah. So that is why you have 4 blah blah or whatever. So 4 blah blah blah. So which means you have four different color. So which means if let's say you have 422, which means you retain two color from the top and two color from the bottom. So which means you have only something like this one. Uh, but these two is same color, this two is same color, this two is another color, this two another color, because you only have 422, okay? Which is written at JAB and describe the number of luminous and chrominance sample. So J is the total number of pixels in horizontal sampling region, and A is the number of pixels sampled at the first row of pixel which is on top, and B is the number of pixels among the second row in the J region. So basically, this is the common structure of chroma subsampling ratio. The first, how many color in color box, I should say. How many color box is there? So that one is J, and the top row is A, the bottom row is B. Okay. So when you have 444, which means you utilize all the color, which means you have four different blocks, and all these color are available. Okay. So this is 444. This is the highest quality for, which means you did not compress anything. Okay. This is the original CB or CR without any compressions. So this is your Luma channel or Y. This is CB and CR. Or lah, CB or CR, which means you have your CB channel according to this one and CR channel according to this one. Okay, so you need to class out. I mean, you need to sum out. For example, RGB, you have R value, submit. I mean, add up with the G value and add up with the B value, so you get the total color images. The same thing happened here. So which means you have this color and add up with this color, so you get this color. Can you see this is sort of light blue color, and this is actually black color. This is actually black color, light blue, and then become dark blue. Not light blue lah, but maybe moderate blue lah. Okay, simply blue lah. But later on, after summer, you get dark blue color, something like that. Okay, so this is orange, but add up with gray color, so you get something sort of brown or some near looks like a gold color, something like that. Okay, so this is the uh, final summations. But nonetheless, the given example is YUV. So this is Y, this is U and V. If let's say it is YCB this is Y, this is CB and CR. Okay, so you just basically sum up everything. So this is the highest quality. Uh, we don't, I mean, in Chroma Subsampling, we don't really so-called improve the quality of image, but rather it is just, uh, compressed or no compressed. So no compressed, which means highest quality. I mean, the Chroma Subsampling never enhance the quality, never enhance. So it is either compressed or so-called subsampling here, or it retain the original quality. So when it say highest quality, it's not that it improves the quality, but instead it perform no compressions. Okay, no subsampling. Okay, it indicates that no chroma subsampling is used. Each pixel is represent and retain its own luminance, which means nothing happened. You retain the own luminance and chroma value. The best video camera will have capability to output 444 chroma. Okay, so ideally we will have 444 chroma lah. Okay, which means you have no compression at all. Mm. So 422. 422, which means you have four different blocks, but now you only have two color available on A row and two color available on your B row. Okay, so which is this one. Okay, this is already fixed by the standard. So which means you are not really selecting the color. Okay, I mean, not to say I want to select, I don't want to cross out the green color. I'll cross out the yellow color instead. I don't want to cross out the light blue. I cross out the uh, peach color, something like that. Okay, not like that lah. Okay, this is a so-called a standard. So so this would be the pattern it is. So it will cross out the green color and also the blue color, and will cross out the pink color and the red color. So what happened to this block? It is using this one. Okay, it is using this color, and this block is using this color as well. Okay, so that is why you would see sort of blue over here, and this is actually the result of uh, black color plus with the or yellow color. So basically, you can see as this, you still have four different blocks, but this block would be, what color is it? Blue. This is blue color, this is blue color, and this is yellow color, this is yellow color, and the bottom one should be peach color, should be this one, peach color, and followed by purple color, maybe this one, something like that. Okay, so it still remain has four blocks lah, but it is not really just cancelled out lah. Because when you cancel out, you plus with something else, right? Uh, you plus with something else, right? So if without any color over here, so basically you are plus. I mean, you're adding some zero lah. So which means you remain the original color. But in fact, it is not lah. It is using two color to represent two different box. Okay, which is blue and blue, yellow and yellow, peach and peach color, purple and purple color. Okay. So the 422 chroma subsampling sample 2 pixels from both the top and bottom row. the reduce this reduce the chroma information to 50% of the uncompressed uh, source chroma. Okay, so 50%, this one is important, is that, I mean, when you have only 2 and 2, so you will able to reduce the CB and CR or UV channel into 50% of its original size. Why? Because you shared out the information. Okay, originally you have 4, right? Now you only have 2, which means 50%. You set up 50%. Okay. So another one would be 420. This should be the highest sampling. Okay, you have 420. So 420, which means the more reduced 420 chroma subsampling takes 2 chroma sample from top A row and none from the top B row. Okay, so which means for this one you have something like this, 2 from the top row, something like this one. Okay, because it is taking it still have four different j, I mean the j number is still remain as 4, but the a row remain as 2 and the b row nothing. So we rule out everything from the bottom, but on top of it, since it remain this blue color and remain this pink color, so sorry, yellow color, so you have your blue color dominate 4 different blocks here and yellow color dominate another 4 different blocks. Okay, so that is why the color over here, it is, I mean, this side is more on blue color and this side is more on yellow color. Okay, because this is how it's being formed. Okay, so instead the bottom row share chroma information from the top. Okay, so the B is actually sharing the chroma information from the top row, and this reduce the overall information to approximate 25% of the uncompressed, uh, reduce to approximate 25% as compared to uncompressed chroma. So which means this one can reduce the original size by 75%. Okay, approximate lah. Okay. So for this one, no compressions. For this one, I mean 422 you reduce by 50% and 420 you reduce by 75%. Okay, another one would be 411. A chroma subsampling of 411 also reduce the amount of chroma to approximate to 25%. So this is also reduced by 75%. It takes one sample from the top row and one sample from the bottom row, which means for this one, since it is remain the blue color, it will be something like this. Okay, you have your four, you still remain the 4 row, sorry, 4 column, just that the top column is only one value and the bottom column is another one. So you have since the standard here is choosing a blue and orange color, so this is it. Okay, so this one also I mean remove or subsample the size and causing the size to retain around 25 of this original. So it takes one sample from the top O row, I mean A row of the pixel and another one sample from the bottom, I mean lower B row pixel. A subsampling of A11 is the subsampling ratio found in DVCAM and also NTSC DV. Okay. Okay, let me recap a bit. So this chroma subsampling you have, this is the general form whereby 4 is referring to the 4 different blocks, 1, 2, 3, 4, and A is the top row, B is the second row. So you have 3 different kind, 1, 2, 3, 4, 4. You have 4 different, yeah, you have 4 different kind of chroma subsampling ratio, which is 444. When you have 444, which means you did not perform any subsampling lah. Okay, everything remain as it is. And if you have 422, which means remain two color at the A row and remain two color at the B row. Okay, so this chroma subsampling will reduce the size by 50%. And you have 420. 420, which means this is A. So which means you have two color from top and zero color from bottom. So which means it shared out the color among all these four color blocks, which is blue and yellow. And this will remove downsample the size by 75%. And another one would be 411. 411, which means you have one color from top and one color from bottom. So for this one, you are also downsampled by 75%. Okay, any question regarding the chroma subsampling? No. International Telecommunication Union Radio Communication Sector ITUR define a standards called CCIR 601 for digitization of video picture. So this is the one of the chroma subsampling lah. Original without chroma subsampling, and bottom is after the chroma subsampling. So this is the effect lah. When you have subsampling, for sure you will have some effect. Just that this effect is it will affect the how they affect the quality of the image. So the top one, it has, no, don't have any chroma subsampling. No chroma subsampling is applied. But the bottom one is already applied by chroma subsampling. So you would found that this is the effect lah. Okay, you can see the effect. I think not much here, but at this transition line lah, you were able to see this kind of effect. Okay, because it is sharing out the chroma value. Um, the continuous slide, these three slides is just for your information, okay? Because you are not going to study this one in depth. In fact, it is also important also, okay? So original digitization format used in CCIR 601 for use in television studio, whereby the circle, the hollow circle shows the pixel with only Y value, and this dot reflects CR and CV, and this which means this is full color Y CV CR. Okay, so this is the pattern for 444, 422, and also 411 and 420. Okay, that is this. Okay, and this is some of the info. Luminance resolutions. This is different standard. CIF and QF, these are different standard. So luminance resolution would be this one, this one just FYI lah. I don't think it's so important. Okay. Any questions? That's all for this chapter, video processing. Yes, no, no. Okay, we take 5 before we proceed to next chapter. Yeah, for those online class, we just have a chit chat over here, and we'll continue later on. We have plenty of time. So, because one of the question, I mean, student asked about the title. So perhaps I can explain a bit. So, when you graduate from degree, you have D, E, and G, right? A Bachelor of Engineering. Some with honors, some without honors. Honors will be better, lah. Okay, which means you have a first class and without first class, something like that. So later on, go for master, and after master, you go for doctorate. So after you go for doctorate, you will get a title DR, doctor, lah. Doctor don't really have any rules and regulation to protect those candidate with doctor, but this title is being very cliche and very well known across the world. So whenever you have doctor, people would put in the title, even though you go for any registrations, for example passport, for example you apply for loan, doctorate is being considered. If you work as a professional field, for example engineer, doctor, lawyer, and etc., your value, I think it's called CTOS. CTOS value is higher, which means it's easier for you to get a loan, something like that. Okay, that is nothing related with the level of working. Nothing related with that. I know. Whatever career you work in, you still can get a very good job. Okay, it's nothing related but to that. But that is the professionalism is part of the criteria to be calculated in your credit card and also loan applied. So that is DR, doctor. So MBOT, MBOT is a Malaysia Board of Technologies, is another board. So when you see the word board, usually it is protected by law. So MBOT is another, I would say recent years, after Dr. Masli Malik, our previous educational ministry, he advocate technology, right? So MBOT after, I think it's somewhere around there, uh, being formalized and established. So it is protected by act. So those that of course there is some examination paper and also interview. After that, 3 years experience, uh, oral interview and paper examination, and then you will get the title TS. So TS is professional technologist. It is more on technology. Okay. So recent year you also aware there are a lot of technology engineering, right? Like BTech and etc. What product development technology, which is the new course in our faculty as well. So that is part of it. And then later on, we have IR. IR is for engineer. So professional engineer. So you get IR, the title IR. So professional engineer is under BM, Board of Engineer Malaysia. Since it is a board, it is protected by another act as well. So that is IR. And IR also you can, I mean, for chemical, mechanical, civil, electrical, and one more, I forgot what it is already. So all these five category, five field can further to get practicing certificate, so-called PE, PC. PE is referring professional engineer, PC is practicing certificate. So which means you can sign the building. For example, okay, I want to endorse this building, it's okay to submit, so you can sign. So who can, I mean, why is this important? For example, if you want to tender a project to Petronas, or Tenaga National Malaysia, if without PEPC, you are not entitled to submit anything. Do you understand? So, which or you want to create a company, engineering company, and you are not PEPC, you cannot create the company. You cannot establish the engineering company. So another title would be AR and SR. AR and SR are for quantity surveyor to survey what is the material need to use to build the building and etc. So that are AR and SR. Okay, there are another things. Okay, more on quantity surveyor, and then associate prof and professor, which is ASAP lah, ASSC, ASSOC prof or AP. And also professor is given by university. So which means maybe Thai you see like Dr. Gokami, he recently get his associate professor. So associate professor is something given by the university. Okay. So if let's say you, I mean, someone no longer work in Thai UC, and this associate prof is actually given by Thai UC, so he no longer can call associate prof lah. It is something like title, for example, senior engineer. So if let's say X company give you the title senior engineer, and you no longer work over there, you maybe you go to another company and work as a cleaner, so you no longer a senior engineer lah, something like that. So but usually people will depends on who give you the title. Some is associate prof and become professor, and later you have some other emeritus professor is given by different ranking people. So that is different. Okay. So that is the difference in terms of title. TS, IR, doctor, associate prof, and professor. Okay. Assistant professor is quite new. Assistant professor is not associate professor. Assistant professor is something very same as senior lecturer. But private U like to use this term. I don't know why. For example, Utah, they don't really have senior lecturer. All are assistant professor. But actually, it's same as the senior lecturer. But they don't really use the word senior lecturer instead. It is so-called a position. So something like that. Okay. So after you work later on, your engineer, you have different ranking. For example, Intel, you have different ranking. For example, rank 1, 2, 3, 4, until 7, I think, until 7. But if you get your master, you will get a different ranking. If you get PhD, you will get rank 6 or 7. Once you go in, you will get 6.5K at least if you are PhD. So usually multinational company, MNC is multinational company, which means the company is from overseas. So all these company usually they very recognized credential. For example, you have master, you have PhD, so they will definitely give you higher salary. But local company is different. Local company is different. They don't even uh, try to get PhD because you know those country which is developed country like Canada, like UK, they will talk about uh, go green, uh, go green is important, this and that, equalization, equality. But those developing country like Malaysia, like India, they're not even earn enough. So it's not that level to top that part. So that is the difference there. Okay. So when you work as MNC, so perhaps, but work in MNC might be not so challenging. Work in local company. Perhaps you can know better. Like last time I worked as MIE, product development engineer, you do a lot of things. But end up you know the entire product life cycle. But if you work in MNC, it's very very difficult. You work only focus only on small part. So usually people will work in local company first for maybe first 10 years, and then later on they go to MNC, planning to retire, something like that. This is the trend in engineering. But end up maybe you are not working in engineering, it's fine. It's okay. But yeah, depends. Depends what you want. Okay, enough talking. Okay, this is our last chapter. This is our last chapter for the MTA, multimedia technology and applications. Okay, table of content need for video compression. Actually, the need for video compression is remain the same. No matter in video, audio, or whatsoever. The needs for video compression is the same. I think I've been repeat for 1,000 times. If let's say this kind of question appear in the examination, I would expect you all know how to answer. Okay, so basic and principle of video compressions. In video compression, we have two different kinds. To be in general, we have two different kinds. The first one is to process solely according to video, which is unique, uh, uh, unique apply to video media. instead of the static image. But another things the another category would be everything you can found in JPEG compression, something like that. Okay, because JPEG compression you can apply to each and every frame. But then when you're comparing different frames, you can have so-called the spatial and also the temporal. Mostly it's temporal with different uh, time taken and video compression standard. So in the image compression, we have image compression standard. I mean, one of it is JPEG law, and then followed by JPEG 2000, which is using DWT. Okay, need for video compressions. Example, HDTV broadcast has a resolution of 1920 multiplied by 1080 at 30 fps using 24 bits to represent primary color. This leads to a total of 1.5 gigabps data rate. But the channel bandwidth is only 6 megahertz. One moment. Okay, but the channel bandwidth is only 6 megahertz that support around 19.2 Mbps data rate only. So channel also has to support audio and other data. So effective data rate reduced to only 18 Mbps. So that is why we have, I mean, when you have HD TV and etc., but your bandwidth is actually cannot accommodate to all, I mean, to supply this data rate. So that is, and also this data is solely for the video alone. It not yet count, I mean, consider in the audio and other transfer of data other supplement data. So that is why after you add in everything, the effective data rate is reduced to only 80 Mbps, which is very small. So therefore, compression required is around 83 times. Is around 83 times. Hence, the compression ratio, this is the compression ratio, which means you need to compress by at least 83 times. So communication network, this is the practical bit rate for the communication network. So over here only mention this slide only mention the needs of compression due to bandwidth. But another thing would be the storage. Okay. But nonetheless, we are not the related industry so-called to really store all those video or multimedia. So if the industrial player that really focus, I mean, this is the main product of their company, so they have to consider how they need to store the data. Okay, how they need to store the video, audio, or eventually the images effectively. It is not about one or two or maybe 100, but up to million. But million is in 1 week time. So 4 weeks you have 4 million. It's not possible, not cost effective lah for you to keep on buying hard disks, this and that to store the data and etc. You need to replace it, but some of the acts, uh, for example, some paperwork, especially in university, some paperwork need to keep up to 7 to 8 years. So how do we keep 7 to 8 years time? This is the things that you need to resolve. And this would some of this is protected by act. So which means you need to comply with the act and you have to store the data for traceability purposes. So basic and principle of video compression. The concept of video compression lies on two main factors. The data in frame is often redundant in space and time, and the human eye resolves the brightness details better than the color detail. Therefore, it is possible to delete some data from the frame with almost no noticeable degradation in image quality. Again, this is lie within the limitation of human eye. So since some of the data is considered as redundancy no matter in space or time, space which means spatial, time which means temporal, those information that is redundancy in terms of space would be high frequency information. Okay, for example, uh, the fast Fourier transform, you remove all this high frequency information, you're still able to understand the information. So of course you cannot remove all lah, but part of it lah. So that is so-called that is actually what is the JPEG is doing. Okay, JPEG compression is doing. And uh, in terms of time, the best we can illustrate is that using the audio processing. So we have so-called the frequency masking and temporal masking, right? So the frequency masking is that you cannot listen to any signal in the masking area, so-called the masker and maskee lah. Okay, so for this would explain the redundancy in terms of time. And human eye are more sensitive towards some of the channel. For example, more sensitive towards the Luma channel and also sensitive towards the Chroma channel. So that is why it's okay for us to remove part of the information selected from this channel which are not so sensitive by human eye. So the main purpose of video compression is to use to reduce the data redundancy and irrelevance. See, redundancy is that you know you have only okay you have only two hand. No, this is not a good example. You have only you have only 1 hour, but you can go for lunch, but you have two different voucher, or you can attend to a concert, but you have two different voucher. So another voucher is considered as redundancy lah, because you have one is more than enough. Irrelevancy is that maybe you you are given something which is not in within your interest. For example, you already have your spec, but then someone give you another spec with different degree. So that one is totally irrelevant to you. Lah. Okay. So this is also called the redundancy and irrelevancy. Redundancy is that you have something which is your interest. You need it, but then it is more than enough. Irrelevancy is that it it only have one, which means the number is very small. It only have one. But this item is irrelevant to you, which means it's not important to you. With or without is okay. Okay. So this is so called irrelevancy. So we have spatial redundancy and also time-based redundancy. Spatial redundancy is the I previous chapter we did talk about the spatial and temporal uh, compressions. So this is the spatial redundancy and time is the temporal. Okay, time and temporal is not really interchangeable but just that it's reflect the same thing. Okay, so in a frame, adjacent pixels are usually correlated. Oh, another thing is that during your examination or maybe in your assignment, when you're doing a video, try not to use the word image, because when you use the image, because in video we have GOI or GOP, group of image. I think it's GOI. I think we will learn this later in this slide. And we have group of image. So group of image is that you group. I mean, in video, it will automatically group some part of the frame as one image. We call it as group of image lah. Okay. So in video processing, try not to use the word image lah, because I'm not really sure you are referring to all the frame within 1 second or each and every frame, because the correct word to be used is frame. So if you're using frame, so for sure you are referring to only one frame in any of the time temporal period. Okay. If you use image, I quite confused what you're using, because some from the lab report, some people are using image, but this image is like I'm really not sure what image you are referring to. Yeah, so is in your examination or in the assignment, try to use the word as it is. For example, in video processing, you use frame instead of image. Okay, we call it as FPS, which means frame per second. So whenever you want to refer to a single static image in a particular time, use as frame. Okay, so in a frame, adjacent pixels are usually correlated. The grass is green in the background of a frame. In spatial redundancy, as I mentioned just now, redundancy is that you have something else, same or very, very similar or eventually identical, but more than enough. Okay. So spatial redundancy is that the first frame, for example, you have because for example you have 30 FPS, 30 FPS. So the computer or the monitor will display 30 different frames in 1 second time. 30. So 1 second is very short, but of course, it's noticeable, lah. Okay, 1 second is very short, but it is noticeable. But all these frame in 1 second, in practical, all these frame are very very similar. But the motion, for example, the horse is running in the very big field. So the motion of this horse would keep on changing, lah. Dynamic change, keep on changing between different frames. For example, 30 FPS. Perhaps the motion of this horse will be keep on changing, but the background would remain the same. This is the redundancy I mean. Okay, mostly in any image, of course, there are some image. For example, you are shooting maybe the ocean. Everything is moving, so that one is okay lah, which means no correlation. But for most of the practical, I mean, most of the practical applications, we have only one subject or many different subject or multiple subject is moving in one frame, and then go to another frame and continuous. But the background usually is remain unchanged or remains some change. I mean, very identical lah. Maybe you are moving your camera or moving your DSLR or moving your mobile phone. So you're shooting something to horizontal, something like that. But nonetheless, the pixel value of the background mostly or usually is very identical. Okay, so this is so-called the spatial redundancy. So we don't really need to keep all the information of this background. If we know that these two images, these two frame, the correlation is very high. Do you all still remember the word correlation? I think we learned this during the spatial filtering, spatial processing. Yeah, spatial processing. We learned about correlation, right? Correlation is actually return a value. For example, GLCM, uh, wear level correlation. So GLCM is actually to return you so-called a value, and this value is actually giving let you know is these two images or these two frame, is it very like, I mean, very same, I mean, the similarity is very high, something like you're turning in. Okay. So if you compare the images of the first and the adjacent frame, and then return you a value. And this value is not only for the entire image, but also the pixel inside. Okay, so by estimating this one, so you would aware that, oh, the intensity of the previous frame, I mean frame one and frame two, is very very likely to get, I mean, the same. So it will migrate the value from frame one to frame two, instead storing different value. Okay, so this is how it's cut down the size of the video in video compression. Okay, and if let's say it's found that, oh, the intensity of this pixel, for example, pixel 1 and 1, is very similar to this one and similar to this one and this one until the 30 frame, the 30th frame, the 30th frame. So it will only keep one information and keep on repeat for 30 times. It is like in your programming, you are calling the same functions for 30 times. So you only need to write one function. For example, you're using im show. So you only need to write, because im show, the im show has its very own function, that all the core function in the MATLAB, it has its own M file, so-called the M file. Okay, so every time you use the call function, it will trigger the M file. It's so-called the functions. So which means you are storing only one algorithm, but you call this algorithm for 30 times. The same thing happened here, which means you have only one pixel holding one information, but you call upon this pixel to display the intensity for 30 times. If let's say you have 30 FPS, okay, so this is the so-called the spatial redundancy. I don't need to store the value. For example, the pixel is 200, 200, and 200. I don't need to store this value for 30 times. Instead, I only store for one time. But I create another algorithm to keep on calling this value for 30 times. So this is so-called the spatial redundancy. Another thing is the temporal redundancy. In the video, adjacent frame are usually correlated. The green background persists frame after frame. Okay, so these two are the very same, but actually it's different. Okay, example of time-based redundancy. This is regarding time-based. So, uh, taking this as an example, you have a moving car near to the building. So we don't really have, let's say we put the, I mean, we set the moving object or the red color car is the foreground. So the rest is the background. So usually you have one character or one object is keep on moving in your video, right? But the background would be remain more or less the same. So adjacent frames are similar and change due to object motion, which is the temporal correlation. So all this data can be remain and is migrate over here. Okay. But of course, it is very ideal to say so, but the background algorithm is very complicated. The background algorithm is very complicated. And if the algorithm is not so well established, you might see or you might aware the image is jumping from one motion to another motion, or it might have overlapping happen. The first and the second frame overlapping phenomenon happen. There are two types of compression, which is spatial redundancy removal and also spatial and temporal redundancy removal. If you are only concerned on the spatial redundancy removal, which means you are talking only one single frame, one frame, okay. And this frame is usually we are talking static frame, okay, which means we have different frame. When we talk about different frame in terms of a timeline T, so we are talking spatial and temporal redundancy removal. If let's say you break down every frame, you only talk about the compression of each and every frame. So we are talking about spatial redundancy removal alone, which is called the JPEG lah. Okay, intra frame coding. This is intra frame and inter frame coding. Video is made of multiple images called frame, which are captured over time. Images have high redundance data as the adjacent image pixels are highly correlated. Each pixel in a frame is represented by three attributes, which is 8-bit, so-called, that is why you have 24-bit later on. And one luminance attribute, two chrominance attribute, which is why CBCR and also YUV, depends on what channel you are using. So Y is the brightness or intensity, which is the luma, and this is the chroma. Chroma. Okay. So luma would be more on the brightness or the intensity. So it would be like you're converting RGB to grayscale, very, very similar to that. But the chrominance channel or CBCR or UV, it is more on color. So you wouldn't see any fine texture, line edges there, but instead it is full with different color. Okay, because this is about color. JPEG compress image, and it can be used to compress frame individually. But more compression can be achieved if using video compression method. So video compression make use of motion compensation to predict a frame from the previous and or for the next frame. Motion vector that describe the transformation from one image to another are applied to the target and synthesis to produce next image. The motion vector, I think in lab, one of the experiment in the lab, it did shows the motion vector, right? You know, you have different kind of this arrow in your image. So that is the motion vector, which means which part of the image is being translated to another position. This motion vector is not really reading your character in your video. but instead it is determining which part of, you have frame one and frame two. It is actually looking at this frame is actually traveling to which part, maybe up, down, bottom. So if let's say this part is traveling to this part, so it will have a motion vector, something like this one, moving for the up 45 degree upwards. Okay. So motion estimation and motion compensation. Motion estimation and motion compensation is very important because if let's say the motion estimation algorithm is very weak, so you would see a jerky, your image is jump from one motion to another motion. It is like something like this one. So this is the frame 66, 69, and then with motion vector. So this is the how this motion vector is being formed is that it is actually correlate calculation the correlation with the adjacent frame, which means you have 66, maybe you calculate with 67, 68, 69, and then you come out with this motion vector. So if let's say predicted frame 69 will be something like this one, okay? Which means you use 66, 67, and 68 to predict something in future. But in fact, this is the real 69 frame. This is the predicted. So this is so-called the this is so-called the when the motion vector is not able to estimate the motion accordingly, you will see this kind of blocky field. Okay, this kind of blocky field, especially this one is very obvious and and the processing of this is also based on 8 times x pixel block. So that is why when you have different or mismatch between different block, you will feel that, oh, why it is very blocky. The images basically you can see something like this one, very blocky field. Okay, and all this blocky field is a result of the motion vector with 40 predictions. Okay, so this is the uh, I mean the frame 69, which is from recording, and this is the predicted. Okay, when you compare, then it is very obvious lah. In video compression, a motion vector is the key element in the motion estimation process. It is it is used to present the macro block in the picture based on the position of this macro block in another picture, called the reference image, so the reference picture. In the video processing, we have different frame, I frame, P frame, and B frame. And all these kind of frame, we have different functions. For example, I frame is the one who act as a reference, which means if you have one I frame and then followed by several P frame and then followed by another B frame and maybe B frame, B frame, okay, and another I frame and continue with P frame, B frame, and then I frame. I frame is the core of the video, whereby it will store it is act as a reference frame. Everything will be reference to that. For example, if you if you are not sure where to get something else, you always ask your mother or maybe your mate, something like that. You always refer to them because they know better. So once this frame is being destroyed, the rest of it would be destroyed as well. Not really destroyed, but would be greatly affected. Perhaps you will see many artifacts on this kind of the adjacent frame. Okay. So compare small segment of two consecutive frame for differences and shows a difference be detected. A, a search is carried out to determine which neighbor segment that the original segment has moved. So which means in one image you have this block, and then this is F1, this is F2, and then this block is being moved to this. So it will actually search the algorithm will search actually where this block is being moved. So after that, it's found that, oh, it is moved upwards 45 degree. So it will show a motion vector like something like this one. Okay. Comparison is made by shifting each of the macro blocks of the two successive picture pixel by pixel in each direction. So it will check pixel by pixel in each direction. So this is the before, after. So previous frame, which is the reference, this is the next target. So which means the this block would be matched from the entire image to check in entire image to know where is this block already moved to. If let's say after checking all this I mean the entire image found that oh there is no correlation at all, which means this block is no longer available there lah. Okay. If let's say after checking oh maybe I found that this block is very highly correlated to here. So the motion vector will be upward, something like that. Okay. So this block is being moved to this part. So the motion vector will be somewhere, something like that. Okay. So this is what I mentioned just now. You have frame 66. So you are using frame 66 to predict frame 69. So this is the original or the normal frame 69. So after you get the motion vector, so you can predict something like this one. Actually, you're still able to predict lah, but just that I mean, how far it is the quality. Sometimes the quality is not there at all, but sometimes it depends on the algorithm. Sometimes it's okay to get the predictions because this kind of prediction is especially important when you have a corrupt video. So when you have a corrupted video, you want to recover the video. This is the method used. Okay, it try to predict whatever happen next, and so on and so forth, and then recover the video. And then from there, it will estimate what is the pixel of this block. So later on, I think you're all aware that there are some of the deep learning algorithm to recover blur image, right? So all these deep learning algorithm to recover the blur image is actually to predict what is the pixel for this particular location. It is like you are predicting something else. For example, you are flipping a coin, you want to predict this is head or tail, something like that. So if let's say you can predict each and every time, which means your algorithm is very good lah. Okay, but nonetheless, we so-called the prediction is that we don't know it is true or not. Okay, it is not, but we have a basic algorithm or basic rules and regulation for us to follow. It is not like okay lah head lah or okay lah tails lah. No, not something like that. But it is something from a series of calculation. But nonetheless, we don't know it is correct or not correct. So we call it as prediction. But prediction is not equivalent to guess. It's different things. So key terms. Prediction of new frame from previous frame are known as forward prediction coding. Previous, okay. Forward prediction coding is that you predict something next or in future, so-called a forward. So you have your reference frame. Always, we always have a reference frame or a reference image. And then you have a target one, and then both of calculate the differences, and then you actually the sequential to predict the frame is very same as the JPEG compression sequence, which means you get the DCT. That is why DCT is important is that DCT always let us to know the frequency information, which is the core of the image, the core of the image structure, I would say the core of the image structure. No matter it is high frequency or low frequency, but it is not understandable by human eye. Just that it is understandable and also processable by the machine language. Okay. So you have quantization, RLE, and Huffman coding. So this is for forward prediction, predictive coding. Previous of next frame is known as reference image, and conversion method works on 16 times 16 is called as the macro blocks. Sometimes work in 8 times 8 as well, depends on the algorithm. But of course, either way lah, 16 or 16 or 8 times 8 lah. It won't be 4 times 4, something like that lah. Okay. Nonetheless, this is the reason why when you have 40 predictions, you will see a bloggy field in your image or no, in your video. So this is the typical video encoder, but I don't think I will explain in deep. And also, I don't really see this as part of the syllabus. But it is very. What I want to highlight is that if you after you learn the JPEG conversions, you will find that all those conversion is more or less the same. Just that there might be different algorithm apply before or after, or maybe they are not using they're not using the ILE, they're not using the what table is it? The table where you get the bit value, but instead they use the Huffman coding and etc. Usually for those that require no loss in data, they use Huffman coding because Huffman coding is a better um, estimations with lossless lah. Okay, so the people are using Huffman as well. So this is the basic um, block diagram for the typical video encoder, but of course you don't need to memorize it. And when you, I mean, in the lecture notes, when you see there is no further explanation, which means it's not so important. Okay, but nonetheless, it's good for you to, to know. Okay, predict a new frame from the previous frame and only code the prediction arrow. Prediction error will be coded using an image code known as a DC. For example, DCT based as in JPEG. And prediction error has smaller energy than the original pixel value and can be coded with fewer bits. This is actually, I'm not sure. Can you all see the theory here is very very similar to DPCM. I think. Is it called DPCM? The one 48 to store the DC value, still remember, for example, 52, for example, 50. So how we actually store it? We store 48, right? And then we store plus 4. We store -2, something like that, right? This is how we store the value for DC, right, in JPEG conversion. The same here. We don't really store the first frame and the second frame, but instead we store the prediction error. Because the prediction error is the prediction error here is that not the error, but the prediction error here is that what is the difference? Okay, so we only store all these +4, -2, and so on and so forth. So which means you have store the first frame, which is the reference frame, and then later on you only store the differences with the first frame, and then another differences with the adjacent frame, another differences as with another frame. So since in particular, let's say we have 30 FPS. So this 30 FPS, which means you have 30 frame in 1 second. So this 30 frame in 1 second should be very similar. Okay, it's not so logic that you have 30 frame, which is totally different, which means it's flashing lah. You flashing many frames in 1 second. Okay, it's not so practical. So all these 30 frames are usually very very similar. So instead, they will only store one reference, the iframe, and then store the differences, so-called the precision arrow, and another one for 30 times, something like that. So this is how to cut off the differences. How to cut off the size of the uh, file, the video file itself. So prediction error has small energy. This energy is that like the acoustic lah. Like the sound wave, you can call it as acoustic, right? So this is you can call it as energy lah. Sometimes in engineering, the energy it means that the intensity we can see this as energy as well, which means you have zero, which means you have zero energy. 255 you have max energy, something like that. Okay, so smaller energy than the original pixel value and can be coded with fewer bits. This is what we want. We want to code something with the least bit possible. But of course, when you code something like this one, it is the algorithm, sophisticated algorithm is required, okay, instead of a very simple one. So use motion compensated prediction to account for object motion. MPEG-2 encode video as a series of picture. So for interlaced sequencer, the two field, still remember interlaced? Interlaced, you have two different field, starting from here, the odd and even frame, and then another one start from here, okay, and continue something like that, zigzag lah, okay. So you have two different field. I think I draw this wrongly. Oh, something like this one. Okay, refer back to the lecture notes. So you have two different field for interlace, and you have odd and even line. So later on, you will combine odd and even line to get the images. So alternatively, they may be coded separately in two field picture. Both frame picture and field picture may be used together in a single interlaced sequence. So high details and limited motion favor frame picture encoding. And field picture always occur in pairs, top bottom or bottom top. This is to ensure continuity in terms of frame. So the output of the decoding process for an interlaced sequence is a series of reconstruct field. So this is actually referring how actually interlaced image is being processed, and I think we already mentioned this in previous lecture lah. Okay, you have different two field, and then all these two field construct to become different line, which is top and bottom, the odd and even line, and then odd and even line join together to form a full frame. Okay, so for progressive sequences of pictures, frame pictures, and the output of the encoding process for a progressive sequence is a series of reconstructed frame. So in video coding, a group of picture, GOP, a group of picture, this is what I meant just now on GOP, as specifies the order in which intra and interframe are arranged. So the GOP is a group of successive picture within a coded video stream. So usually we will actually group the frame, different frame. Of course, we are talking, FPS. So which means you have fixed FPS in 1 second. But we can actually group a series of frames, perhaps 1 second or more than 1 second as one group. And we call it a GOP, group of a picture. So this group of picture is actually referring to they are using the same reference frame, which means you have uh, in one family you have your mother, father, and son, and sibling, and etc. So everything is related to the parents. So the parents will be the I frame, and the rest of it will be the P frame and also the B frame, something like that. So one family and another family can join together and become one community. Okay, but one family and another family is not really the same thing. Okay, so this is the difference. So group of picture is that you have different group of picture to join together to form a full video. But nonetheless, this group of picture and another group of picture is not really the same. Okay, because they are referring to different origin. They have their own different origin. So the successive, we have this is so-called the I frame, P frame, and also B frame. So I frame is something so-called the parents, which means it is the reference frame. P and B frame are the estimated motion compensation compensated frame derived from maybe I frame or maybe from another P frame. Okay, so the successive picture within a coded video stream of film can contain the following picture type, which is the I frame, P frame, and also the B frame. So the iframe, each GOP begin with this type of picture. So iframe is the core of the group, okay, whereby you have, for example, you have something like iframe. So you have maybe different P, and this P you can have different P again, and this P you can get B, and B. So once this is being destroyed, the rest of it will be affected. Okay, so that is why when you have your iframe destroyer, the entire, I mean, maybe the 1 or 2 second is black out, something like that, or with a lot of artifacts. Okay, but if let's say you have only uh but let's say the iframe is not destroyed, but the P frame is destroyed, any of the P frame is destroyed, the rest of the succeeding P frame or I frame, sorry, P frame or B frame, which is dependence on this P frame, will be destroyed. Okay, can you see the relationship over there? Okay, so this is the logic, which means everything depends on it, it will be destroyed. Okay, so P frame, each GOP began with this type of frame. Sometimes we call the iframe as reference picture as well. So P frame contain motion compensated different information related to previous decode picture, and B frame contain motion compensated difference information relative to both previous and future decode picture. So iframe is the reference. It does not depend on anything. P frame, it depends on previous. It depends on previous decoded, and B frame is depends on previous and future. Okay, please do not confuse with this one. Because this will affect their functions. Okay, iframe is the reference, which is never depends on anyone. P frame will depends on previous decode picture. Usually it is a P or I frame. And B frame would be decoded by using both previous and future. So I frame, intra frame, independence frame, which means it is also a reference. It is also a reference frame coded without reference to other frame. Okay, it is so-called a dependence frame. It can stand alone. You don't need any other frame to represent it. So the level of compression obtained with iframe is relatively small because we need all the information in this iframe. So usually we don't have, if let's say we need to compress the iframe, the compression is very, very small. Else, usually we don't compress the iframe. Okay. If an iframe is corrupted during transmission, the succeeding P frame which are based on the corrupted iframe will be affected and error propagate will occur. Error propagation, which means I am affected by the iframe. So anything dependent on me will be affected as well. Okay, I will propagate these arrows to the next succeeding frame, which is depends on me. So therefore, iframe are inserted at regular interval to reduce error propagation due to corrupted iframe. So usually in one video, let's say you have a 4-second video, 4, 3, 2, 1. The iframe will be inserted into the video on a fixed interval. Maybe this one, maybe insert here, 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 and here. Okay, because this is to avoid if this one is being destroyed, the rest of it, the starting from here onwards, is safe. If let's say the whole, I mean the entire video is only depends on one iframe, which means the only iframe is destroyed, the entire video will be corrupt. Okay, so this is very dangerous. It is actually like the circuit in our house, either series or parallel. Okay, if series one light bulb off, I mean burn off, the entire house is burned down. Okay, so this is the difference. Okay, therefore yeah. So iframe you have YCBCR for each of the macro blocks, which is 8 times 8 or 16 times 16. So sometimes I put 8 times 8, but sometimes it's 16 times 16. Okay, interchangeable. Same goes to the JPEG. But nonetheless, in JPEG, usually we are using 8 times 8. We seldom use 16 times 16. Okay, so you have the flow, which is very similar, which is DCT, quantization, entropy coding. So you get your binary code. Okay, so P frame, predictive coding frame. So not independence. Not independence is that it must depends on another I or P frame. Okay, for example, you have I frame and then followed by P frame, followed by P frame, followed by P frame. So which means this P frame can depends on I frame, or it, for example, this P frame, it is depends on this P frame. So P frame can be depends on I or P, but never B, okay. So coded by a forward predictive coding, current macro block is predicted from the similar macro block in previous I or P frame, and the difference between macro block is coded. Okay, so always we always code the difference only. We don't really keep the entire frame. We code the difference. If the difference is big, then we keep the big difference. But the difference is usually very small, because as I mentioned previously, usually we don't have a very big gap between different the succeeding frame, the adjacent frame. Usually the difference is very small. So P frame are encoded by using combination of motion estimations and motion compensation. So higher level of compression can be obtained with them. So this actually the flow is more or less the same to code it. So this is let me see okay, this is just to illustrate how P frame is being coded. So you have your original frame here, and then you get your motion predicted. So these are the, I mean, these are the information being stored because you only store the motion prediction error or the differences between the first and the second frame or the first and the adjacent frame. It never store the entire image, which is the current image. So it store only the um, differences over that. And then later on, from these differences, we will generate this motion vector. And from this motion vector, we can base on this motion vector and in conjunction with the original frame, we can have our predicted frame. Okay. Reconstruct frame one and reconstruct frame two. So basically, this is what we store lah. We store this one. Okay, we store the motion prediction arrow, and then from this prediction arrow, every time we will from this we reconstruct the succeeding frame. The idea is same like how we store the DC value in JPEG. So MFrame introduced a new B frame. So B frame is referring to bidirectional predicted coded frame. Um, when the question asks bidirectional predicted coded frame, I hope you all know it is a B frame. Okay, because these two are interchangeable, and not a must it is given B frame. Sometimes we don't use B frame, we use bidirectional predictive coded frame. Okay. Oh, another thing is in your examinations, if you want to use the short, abbreviations, it's okay for you to use. Uh, but try to define. But for those abbreviation which is very common, like DCT, DWT, is okay. Sometimes you try not to use some abbreviation which is not so common. I don't know what it is. Okay. Maybe sometimes you use uh, I don't know lah. Many different abbreviation which I may not know lah. Okay, so it's best for you to use those abbreviation which is common. It's okay if you don't define. I won't deduct marks for that lah. Like JPEG, you don't every time need to write the join photograph that no need lah. MPEG as well. Seldom I don't see you all write MPEG lah because I think you are not so sure what is MPEG. Okay, so for all these, it's okay for you to use abbreviation. But for those uncommon one, please define first. Okay. Define is not. I not really will deduct your marks from there lah. Just that I want to know what it is. If not, it's very difficult for me to do the marking. Okay. So B frame, I frame, P frame, and B frame is okay for you to use as it is. Okay, it's easier. Okay. So provide the highest level of compression. Due to unexpected motion in real scene, the target block may not have a good matching in previous time. So B frame is coded with reference to both previous and future reference frame, either I or P. B frame cannot be decoded without succeeding P or I frame. So which means B frame is the weakest one. We have I frame first, followed by P frame, followed by B frame. The P frame is only coded using I frame or the succeeding P frame. For example, I followed by P followed by P. So I frame can be coded using I frame. P frame can be coded using the I frame in the previous one, or it can be coded by using the P frame from the previous. But it will never depends on any B frame. Never. Okay. B frame is actually so-called a bidirectional, which means it needs information from previous and future. For example, this is P or I, this is I or P. Okay, it will need to depends on the previous one and future. It's because we want to get the information from both of these. The sample will be here. So you have your iframe here, and then you have your P frame, which is the next one, and then another the B frame, and this is the next. Okay, at least this is the first, second, third, fourth. When we are looking at this one, B frame, it is actually getting information from the previous one. Previous and also the future one. So look at this one. It only get the information. All these three dots is from the previous iframe, but for this one, it get these three dots from this previous P frame, and this dot from the next the future iframe. So later on when it's combined, it has four dots, four different dots. Okay, so these four different dots, but actually this one the position of this dot for the first the position of the first dot is being it's moved already lah, nearer to the Pac-Man, the mouth of the Pac-Man. Okay, so this is something new and it's migrate to this B frame. So but P frame will never get something in future. P frame will never get something from the next future adjacent frame. So this is the difference. Okay, and the compression ratio in the B is the highest. P is later on. I will be minimal. Okay, so this is the differences between IP and B frame lah. Okay, so any question before we end? We will stop here. No? Okay. If no, then that's all. This week we don't have tutorial. We have only 1 hour class on Thursday 1 to 2. Okay, and that's all for today. Thank you.